So if we're to plot this, I'm going to switch to a different color because this one is starting to be a bit dim. Just moving around so that hopefully eventually it becomes possible to see what I've written. Okay. So if we have neutron-proton interactions, or a neutron-neutron, what does the potential look like? It looks like this. So this is R, this is the potential. It looks like that. Okay. So here, this region, this is where it's repulsive. Here is where it's strongly attractive inside this potential well. And then over here, in this region, it dies off quickly. So this actually looks a lot like a square well. This and the next example. So, copy this down and erase it. So for proton-proton, the potential looks like this. We have another hump here. And so here, this is the strong nuclear force dominating. Right? Again, as before, repulsive, strongly attractive, and then dying off really quickly. But then over here, we have electrostatic forces dominate, the repulsive force between the protons themselves. So one thing about this is that nucleons that are in this potential well are fairly free to sort of move around, right? You notice that there's not much slope down here. Right? We got strongly repulsive, strongly attractive, but in that middle region, they're free to move around. This is called asymptotic freedom, right? They can kind of bounce around and exist in their own little kind of box almost, but it's very difficult for them to get closer to one another or to get out, right? To tunnel out. So what's the reason for all of this complexity? My cat has no chill today. I was teaching my other class and I put something on the table and he snuck up and took it off. Okay. What's the reason for all this complexity? Well, as I mentioned before, the strong nuclear force directly binds gluons together. Okay. This is oftentimes called the color force because there's different colors of gluons. And the subdiscipline of physics related to this is called chromodynamics, which sounds like something from like Dungeons and Dragons or something. But the nuclear force as it exists at the level of the nucleons themselves is sort of a residual force. And in order to save time, I'm going to draw it while I have this thing paused because it does take a while to draw. Okay, it's good that I was able to pause because it took me an absurdly long amount of time to draw this diagram. Okay, so what does all this multicolored nonsense mean? So this bit down here is what's called a Feynman diagram, and it's in fact a really complicated Feynman diagram. So let's take some simpler ones. So if you've never seen a Feynman diagram before, they represent particle interactions or scattering amplitudes of subatomic particles. Okay, so it is a way to visually represent the things that can happen to individual particles. Okay, so this is sort of the most basic Feynman diagram here. we'll cover this a bit up. Feynman diagrams are made up of a series of vertices where different particles come together and can change into each other and do various things. So each of these vertices represents something essentially that can happen, and there are sets of conservation laws and ways to calculate how likely each of these interactions are, and then therefore how likely it is that whatever broader interaction you're talking about in total has taken place. So here's the simplest Feynman diagram you can draw. The simplest two-vertex Feynman diagram you can draw. You can have an electron and positron come together and turn into a photon, right? The electron, positron annihilate one another, get turned into pure energy, get turned into a photon, and that photon itself has some chance to turn back into an electron and positron, right? So this could be a electron-positron scattering diagram, right? One of the things that allows an electron-positron scattering, okay? The laws for Feynman diagrams are the laws about these vertices, right? So you can think of these as building blocks, and you can build up a more complicated interaction based on how you can sort of fit together these other various diagrams sort of as puzzle pieces, like, or Legos or something like that. So the important thing to note is that time flows this way, right? And then this does not represent a spatial dimension. This is just there, okay? There's where things are on this side of, or in this dimension doesn't mean anything. Another possibility for interaction is that we have two quarks. So there are, oh god, I forget how many types of quarks there are. There's a lot. They have weird names like up, down, strange, charm, a few others. Right now we're just talking about ups and downs, right? A proton is two ups and a down. A neutron is two downs and an up, okay? So say a down quark, two down quarks are coming in at each other. They can turn into a gluon, and the gluon then has a vertex with two ups. Likewise, gluons can connect two downs or two ups, right, on either side. So I could have green on either side. Okay. So it's basically, these are the particle interactions that can happen. All right. Now let's examine the case that we have a proton and a neutron, and they're going to interact. Okay. So what happens is we've got the proton and neutron, and they're going to interact via the gluon up-down quark interchange action. So the first thing you notice about this is that it's not something like this where we have some ephemeral particle like a photon or a gluon that's being exchanged, and this creates the force between them, right? We have this diagram where they're kind of switching quarks between themselves and then going off on their merry way. So these two up quarks, right? This first up quark interacts via a gluon with the down quark, and this produces a down quark that's sort of flying off into space, okay? These other two up quarks, or this other up quark, right, then interacts via a gluon with a down quark that came from the neutron, right? And then this down quark interacts via a gluon with this up quark and then continues on as the down quark of the neutron. So the proton exchanges a down quark with the neutron, and then likewise a down quark from the neutron gets exchanged via a similar interaction with a down quark from the proton. And then, where to put it? These two down quarks interact, or no, this middle down quark continues on and remains part of the neutron. So only this down quark here and this up quark here don't interact outside of their own constituent particle inside their own nucleon. Okay? So this particle, constituent particle that's made of a down quark and a down quark from the proton and a down quark from the neutron, is what's called a neutral pion, which is a subatomic particle. So this gives you an idea why the strong nuclear force is so complicated, because it's not something that's mediated simply through a single particle, right? the photon mediates the electromagnetic interaction. The gluon mediates the strong nuclear interaction directly, but a proton and a neutron interact via this more complicated process. Okay. So these particles that mediate exchanges, here the pion, here the photon, here the gluon, they're called virtual particles. Okay, the book goes into a bit more detail about what virtual particles are. Whether virtual particles are real or not is something that can be debated. Essentially, they become real in the case that they interact with something, but otherwise they are not real. Okay, if that's confusing, then it's quantum physics, it's confusing. Okay. So, I'm not going to dig too much deeper into this, despite the fact that it took me like 15 minutes to draw this diagram. But hopefully this demonstrates to you why the strong nuclear force is still not totally understood, because it's not a fundamental interaction, it's a residual or composite interaction. Okay. I feel bad erasing it. I spent so much time drawing it. Still got 20, 30 minutes. Okay. So, we know that there's lots of energy stored up in the nucleus. You can see this very directly, that we know that work, which is change in energy, is equal to force times distance. Right? So the strong nuclear force is the strongest force. It is 137 times the E&M force, and 10 to the 38 times the gravitational force. Okay. So we know that we can transform energy into matter and matter into energy. So since what we're playing with when we're playing this equation is the strong nuclear force, the strongest force, right? You can think of perhaps you're releasing some binding energy. There's lots of processes that release energy from the nucleus, but you can think of perhaps this is some binding energy where all I've done is taken two particles apart and all of a sudden they have a lot more kinetic energy because they're releasing that energy that was stored in when I put them together in that electrostatic repulsive way before they got locked together by the nuclear force. So when we unlock that nuclear energy, you might ask, well, how much energy is that? So let's take 1 gram of matter and imagine we turn it directly into energy. What could we do with that? Well, that is 1 gram of energy. 1 gram gives us energy. So 0.01 times 9 times 10 to the 14 joules. Okay. What? How did I not write down the... Okay, well I can just do that because it's just moving a decimal point over. 9 times 10 to the 1, 2, 10 to the 12. Okay. So let's try and get an idea for how much 9 times 10 to the 12 joules is. Okay. So again, this is the energy we get from 1 gram. So let's take an aircraft carrier, right? Wrote down a Nimitz class aircraft carrier. So mass of aircraft carrier is about 9.7 times 10 to the 7 kilograms. Okay. And let's think, how much energy would it take to grab this aircraft carrier and then via whatever mechanism put it up into orbit next to the International Space Station? How much energy would it take to lift an aircraft carrier into low Earth orbit? So energy equals mgh, and we're not taking the 1 over our version of gravitational potential energy. It's low Earth orbit, it's still pretty close. All right. So let's say International Space Station is, what did I write this down? It's very confused notes, I apologize. Yes. 400 times 10 to the 3 meters. Okay. So, if we took this amount of energy, right? Oh no, this is the opposite way. No, that's right. If we took this amount of energy from 1 gram, right, it would be enough to take 2.5 Nimitz-class aircraft carriers and put them into low Earth orbit. Right? So 1 gram of matter turned into pure energy could do that if we could build all those chains of mechanisms that would allow that to happen. Okay. So of course we have 2 ways of turning mass into energy, and that is nuclear power, as you would see in a reactor, and nuclear weapons. Okay, so let's talk a little bit about where that energy comes from and how it's released. Well, the mechanism is fission. So fission is when we break apart an entire nucleus into other pieces and we have new constituent elements, right? So if we have the uranium isotope, U-235, we can take a neutron and fire it at that U-235 nucleus. So U-235, which has 92 protons, 143 neutrons. So we fire that neutron at that U-235 nucleus, and this turns into a barium nucleus flying off, a krypton nucleus flying off, and then 3 more neutrons, and a bunch of high energy photons. Right. Okay. So via this fissile reaction, we release energy not just of the kinetic energy of the resultant particles, but also a lot of electromagnetic radiation in the form of high energy gamma rays and probably other frequencies as well. Okay. So to write this as a chemical reaction, so this is U-235 fission. Neutron plus U-235, krypton 91, barium 142, plus 3 neutrons plus electromagnetic radiation photons. Okay. So what happens is that this interaction not only breaks apart the U-235 nucleus, but releases 3 more neutrons. Well, what if there's more uranium-235 nuclei around? Well, then those neutrons can hit those uranium-235 nuclei, and this, of course, is what's called a chain reaction, right? So we can make chain reactions manually, essentially, just by getting enough uranium-235 together in the same place. Okay? Uranium doesn't mostly come naturally in this isotope. It's mixed up in the ground with lots of other isotopes, So we have a reduced likelihood that these neutrons are going to hit another uranium-235 nucleus because it's in a sense contaminated with other uranium isotopes and probably also other atoms that are mixed up in whatever natural ore there is. So if we want to create a sustained reaction with uranium-235, we have to refine it, right? We have to turn that uranium into the purest type of this isotope we can get, so that these neutrons, when they fly off from one nuclear reaction, start more nuclear reactions and make a chain reaction. So there have been, and I think continues to be at least one, known natural uranium reactors that exist in the Earth. They just produce heat continually. It's because by chance there happened to be a concentration of U-235 in this place. If you want to make a nuclear reactor or a nuclear weapon, what you need to do is refine this uranium-235. And the way that this is typically done is with gas centrifuges, right? You turn the ore essentially into a gas, you spin the centrifuge, which separates out the particles by their masses, and eventually you can get enough uranium-235 to do whatever you want to do with uranium-235. I'm not going to tell you what to do with your uranium. And don't tell me to do what to do with my uranium either. So there's a few interesting stories about this. As physics majors, you've probably heard at least a few of them. When they were first experimenting with uranium-235 and trying to create sustained nuclear reactions during the Manhattan Project, one of the things they actually did, which today is terrifying, is they just took two spheres of uranium, or rather two hemispheres of uranium, half a sphere, and stuck them together to see what happens. Well, why is this so dangerous? Well, first, if you get enough uranium in the same place, you're going to increase the rate of these reactions because you're going to have more neutrons, more uranium-235 atoms, and eventually, if you put enough uranium in the same place, this reaction doesn't stop, okay? It keeps going. The amount of uranium you need to create a sustained nuclear chain reaction is called critical mass. And once you've just put enough uranium in one place that it reaches a critical mass, well then it's going to continue to burn essentially. And if that rate of burn is quick enough, it will explode into a nuclear detonation. So when people were first experimenting during the Manhattan Project, they had a lead brick wall. They had these two spheres, and then someone just reached around the lead wall and with a screwdriver was moving these two spheres apart, right, to measure the rate of radiation when they were it depended on how far apart these spheres were. So they were trying to find their critical mass, actually, and the guy slipped, and the spheres came into contact, and who knew what was going to happen? So the guy went around and knocked the spheres with his hand apart so that the reaction would stop. And he said, everyone drop something on the ground and leave. And then he went and calculated essentially everyone's radiation dosages and said, well, everyone else should be okay. I've gotten a lethal dose. And he later died of radiation poisoning, which is a really terrible way to die. That same core of uranium that was called the demon core, and it actually later killed somebody else, but I don't know the story behind that one. This is one of the ways you can make nuclear energy. The other is with the opposite process. Instead of blowing atoms apart, you can stick them together. Okay? So this is called fusion. There's lots of different fusion reactions. I'll just write down one. So we've got H2, H3, and they can combine to make helium-4 plus a neutron plus lots of thermal energy. So people make fusion bombs by just putting deuterium and tritium, H2 and H3, around another existing nuclear weapon, which in the simplest case, for example, what was the first atomic bomb? Little Boy. Yeah, Little Boy was what's called a gun-type nuclear reactor, where they had a brick of uranium-235 and then a bullet of uranium-235, and the bullet just got fired into the brick, and then that was enough to make critical mass. And the other one, Fat Boy, was an implosion type, so it symmetrically collapsed in, which apparently gives you better destructive efficiency, as grim as that is. And if you want to make a fusion weapon, you just have to get some tritium and deuterium and mix them up in there. And when the other nuclear reactions go off, that's enough to fuse the tritium and deuterium together. Really, all you have to do to get these guys to fuse is just to get them smashed into each other, right, at the individual nuclear level, which sounds simple, but of course it's not. At least not to do in a controlled way. So you combine these elements, fuse them together, and you get helium and neutron and lots of thermal energy. So the best example of a sustained fusion reaction, of course, is the sun. Right? The sun is a giant ball of hydrogen which is slowly turning itself into helium, okay? Releasing more thermal energy, which, you know, thermal energy is the motion of the constituent particles. So the more thermal energy you have, the more likely that these atoms are going to slam together in the right way, and then you create more reactions, right? Of course, the problem is if you want to do this in a sustained way, generate power, like they're doing with the various fusion projects all over the world, is, well, how do you build a box that this stuff burns in, essentially? And the answer is either you use inertial confinement, where you just fire a pellet into a chamber, lasers blast it, and that creates a momentary fusion reaction, or you have a tokamak type reactor where those gases, those superheated gases, are held in place by an electromagnetic field, right? Because if they could come into contact with anything, they just dissolve, and these gases would de-excite, and et cetera, et cetera. Yeah. So that's an active area of research and has been for some time, because unlike fission, this is pretty clean, right? There's not really any waste products, and the radioactivity that's generated is very short-lived compared to how long-lived the residuals are from a fission reaction. And it would also be much safer, despite the fact that these reactions are typically more energetic in total. You have to keep everything confined, and if you have a runaway reaction and the plasma breaches the chamber, well, then the thing just stops working because the magnetic containment is ruined, and just, I mean, you might melt the device itself, but you wouldn't destroy a city or anything like that. So, an active field of research, and has been for a long time because of the great promise of it, but again, it's extraordinarily difficult. Recent advances have been made. For example, one really cool thing to look up is a German research group, maybe a few years ago, designed something called a stellarator. So the neat thing about stellarator is that the plasma that's, you know, the plasma that is the nuclear reaction, that is the fusion nuclear reaction, itself generates the magnetic field that contains itself. So that's kind of neat. It's really cool because it wasn't designed by a person, it was designed by a computer, because these plasma fluid mechanics, it's called magnetohydrodynamics, are very complicated. I mean, it's inherently nonlinear because imagine you're talking about a charged fluid, essentially, so it moving around is the thing that generates the field that affects itself, that causes it to move around. So it's complicated. So this thing was designed via some machine learning type process. I don't know if it was machine learning, it could have been genetic algorithms or whatever else. So it looks like it was designed by aliens. It's this weird curvy kind of thing. So I recommend you go look at a picture of it. It's pretty cool looking. But despite the fact that fusion is really difficult to do on Earth, that happens in stars all the time. And one important thing having to do with stellar evolution is what's called the CNO cycle. Okay, so this isn't the only fusion reaction that can happen. It's one of many hydrogen fusion reactions that can happen. And then there are more fusion reactions that occur once you get to heavier and heavier elements. So the CNO cycle starts with hydrogen. Hydrogen gets fused into helium. Helium gets fused into carbon. Carbon fuses into nitrogen. Nitrogen fuses into oxygen. And oxygen fuses into iron. So when the universe was created roughly 13 to 14 billion years ago, mostly it was just hydrogen. Very, very small amounts of helium or anything else. Nothing really appreciable. Okay? So the universe started off as all hydrogen. And stars evolved, collapsed, and burned, and that allows hydrogen to fuse into helium. Now, if that star is large and hot enough, well then more fusion reactions can take place, more energetic fusion reactions can take place. Helium can turn to carbon. If that star is massive, more massive still, it can turn to nitrogen, then oxygen, and then iron. So in fact,